It's Paul with a script that combines real-world data sets with continuous models. And the first idea I want to take up is what happens if you take a function of the random variable. In the lectures, you have seen some examples of how you can generate a random variable in accordance with some distribution, then take a function of that random variable and get a new distribution. So we'll try the same idea. We'll generate a random variable x that's uniformly distributed on the interval from 0 to 1, take the logarithm of that random variable, throw on a minus sign, and it is proved in the lecture notes that the resulting random variable has an exponential distribution. Here we're going to try that out. So let's generate 100,000 samples of a random variable x that's uniformly distributed in 0 to 1. There you see a few of them. Now if y is equal to minus log x, all I have to do is exploit the fact that log is a vectorized function in R, and I get logarithms, and you can see a substantial number of these are greater than 1. If I plot a histogram of them, well, it does seem to fall off exponentially, and if I overlay a plot of the exponential distribution, LWD is short for line width. That's what gives me this nice, thick and lovely red line. You can see there's a beautiful matchup. Now let me repeat an example from Chihara and Hesterberg that you've seen earlier. Here's some data on numbers that are believed to comply with an exponential distribution and the number of samples that fall in various bins. And the general strategy is, let's take a function of this random variable that would be uniformly distributed. In that case, the function would be, we take the exponential of minus y, and we can compute the necessary bin sizes by just taking the exponentials of various values of y, 0.25, 0.75, 1.25, and so on. Now once we form this function, the observation should be uniformly distributed, so it's very easy to calculate the expected number in each of these bins. And if you look, you'll see this was just another way of doing the same calculation we did in a different script a week ago. But now here's a case where we haven't seen the density function yet. What I'm going to do is generate 3 samples from a uniform distribution in 0 to 1, and then select the largest of the 3. So someone takes a test where he or she has an equal probability of getting any score from 0 to 1, but only submits the largest of the 3 test scores. We'll set up a numeric vector to hold the results of doing this 10,000 times, do it 10,000 times, and plot the histogram, and look at it. It looks vaguely parabolic. It's going from 0 to 1. Well, a function that is parabolic, goes from 0 to 1 and has an integral of 1, is 3x squared. Let's plot that function, and it does match very nicely. Now it turns out this distribution is available in R. It's just one that you haven't met yet. It's a special case of a beta distribution, and here I plot the density function for the beta distribution of x, where the parameters are 3 and 1. That will give me something that is proportional to x squared. 5 and 1 would give me something proportional to x to the 4th. If the first parameter is 1 and the second one is a larger integer, we'll get something that is sort of backwards, like a power of 1 minus x. So I will plot this from 0 to 1, and it overlies my previous red curve perfectly, showing that this is the same function. Now, let's figure out what function will make the distribution uniform. We know the density function, it's 3x squared. The distribution function is therefore x cubed. In other words, the probability that the random variable x is less than some value little x is x cubed. Let's give x cubed a new name. Let's call it z. So the probability that the random variable x cubed is less than little x cubed is equal to little x cubed, or the probability that is less than z is equal to, let's fix that, z. Okay, now we're almost there. So, what I've concluded is that if I take the cube of the random variable x, I should end up with something that has a uniform distribution. Let's try that. Okay, cube maxes is a numeric vector with 10,000 slots, and I will fill it in by generating 3 random numbers between 0 and 1, taking the largest of them and cubing the result. And bingo! A histogram of the results looks very nearly uniform. This can be a very useful trick for data analysis. You carry out a function on your samples, which, if your model is correct, will make the resulting distribution look uniform, and it's much easier to spot when something is plausibly uniform than to spot when it's plausibly Poisson or exponential or gamma. Next, let's start looking into the normal distribution. This is a lead-in eventually to the central limit theorem, and what we're going to start with is Texas babies. So we'll read in a file that contains the weights and other data about babies born in Texas back in 2004. There might well be an interesting term project in here because the gender of the baby is specified, whether or not the mother was a smoker, how old the mother is, and so on. But we're only interested in the weights. I get tired of typing something this long, so let's just copy it into a vector named ounces and look at a histogram. And some folks would say, oh, that's got a big bump in the middle and tails on the side. It looks kind of like a bell curve. Let's check that hypothesis. First, we'd better take the length of that vector to find out the number of babies. And then if we think that a normal distribution fits it, we'll find the right parameters for that normal distribution, the mean, and the standard deviation. While we generally talk about variances, the parameter that's used for the normal distribution is the square root of the variance, or the standard deviation. Well, that does have a bump in the middle at the right place. It's got a bump in the middle at the right place because we made the means match, and it's got roughly the right width because we used the same standard deviation. But we want to do a more careful comparison, and here a good idea is to use the so-called deciles of the distribution. The number of counts in 0 to 10%, 10 to 20%, and so on. And for the normal distribution, the function you want to use is called Q-norm, Q for quantiles. So Q with mu and sigma as parameters and 0.1 gives you the value that corresponds to 10% of the normal distribution. I can check that by asking what is the probability that this value, 25, 75, has the property that a normally distributed random variable with our mu and sigma is less than or equal to n1, and we get back the answer. It's 10%. What about the babies? Well, we set up something that's true, i.e. 1, if the number of ounces of baby weight is less than n1. Take the mean of that, and we get about 0.08. Not too bad. Let's try it with a whole vector. All I have to do is call qnorm with the first argument that goes from 0 to 1 in increments of 0.1, and then compute the expected number of babies in each bin, which is just 1/10 of the babies in each bin. And you look at these and you see, this is not quite as good as we'd like. Because if this were uniformly distributed, we'd have roughly 159 babies in each bin. We've got far more babies in the middle, and we've got fewer babies out on the edges. And in fact, if you look at this distribution, you see that's the problem. The peaks are too high, and the tails are too small. If we want to be more formal about this, we can use a chi-squared test. So all we do is take the observed number of babies minus the expected in each decile of the normal distribution, square it, divided by the expected number, and that gives us a value that is 69 and change. Now, it's true, we use 10 bins. We have to subtract 1 because we made the totals match, but we also estimated 2 parameters. We estimated the mean and the standard deviation for our normal distribution. That costs us 2 more parameters. So the fair comparison is to use d chi-squared with 7 degrees of freedom. That's got a density function that looks like that. Here's our result, way out on the rim. The probability of getting that large a discrepancy just by chance is next to nothing. The notion that these baby birth weights are normally distributed is ludicrous, and in fact, there's no physical or biological reason why it should be so. But now let me show you a way of getting something that is reliably normally distributed. I'm going to set up a numeric vector, empty initially, to hold the means of samples of the weights of 25 babies. So let's check that this works. 2,000 times I will assign to the ith element in this vector the mean of a sample of 25 babies. This will be drawn without replacement, so it'll be 25 different babies. Let's plot a histogram of that. Now this is looking a bit more bell curve-like, and we can test that hypothesis by computing its mean. Well, big surprise, the mean of samples of 25 is the same mean that we had before. That's not going to change. And in fact, for the standard deviation, which was 551 for the individual babies, is smaller by a factor of 5. That was predictable on theoretical grounds. If I plot a graph of the density function for the normal distribution over a reasonable range of baby weights, that matches the histogram much, much better. And if we want to confirm that it's much, much better, we play the same game as before, using the deciles of the normal distribution, make a decile bin plot for the normal distribution, compare the observed number of babies in each, of sample means in each decile with what we've got. And now you can see they really match much more nicely. We expected to have 200 in each bin. It's true, sometimes we're up as high as 221, sometimes we're down in the 180s, But when I compute chi-squared and display it, you can see that there's a significant probability of getting a larger value by chance. So in this case, the normal distribution is a reasonably good model. And if I do this again, drawing different samples, that won't take long to do. You get a different result each time. This is going to turn out to be a consequence of the central limit theorem, even if your initial distribution isn't well modeled by a normal distribution. If you take the mean of a large sample, that's going to be approximately normally distributed. Now, there's another quick and dirty way of testing this. Here we have the deciles for the normal distribution. We have a sequence that runs from 0 to 1 in increments of 0.1. Here, for comparison, we've computed the quantiles for the baby weights, again using the same sequence. This type equals 2 is there because in the case of discrete distributions, there are a number of different possible conventions for quantiles, and I decided I liked number 2 the best. Now I can plot one of these against the other. So I'm going to plot the deciles for the normal distribution against the quantiles for the baby weight distribution. And if there's a perfect matchup, they should lie on a straight line. It took me a while to find out that curve will not take x as a formula for a function for its first argument, but it turns out to be happy with x plus 1 minus 1. And that doesn't really lie very well along a straight line. It's above the line here, below the line there. If, on the other hand, I use the means for samples of 25 and do exactly the same thing, now the points lie almost perfectly on a straight line. So this is an accepted way of comparing something with a normal distribution, and it's been automated. All you have to do is take something like ounces that you think is a good match to a normal distribution, if it is, you'll get a straight line. If it isn't, you'll get a curve like this. So this tells us that the weights of individual babies are not well modeled by a normal distribution, but the mean weight of 25 babies is pretty well modified by a normal distribution.